Welcome to EDU World Space.
So for this problem, we'll need to keep our eye on the figure that's shown with the circles. So here, let's start off by using the fact that this triangle PRA is a right triangle.
Here's a clean and professionally formatted presentation of the calculation
So
shown in
if
the
we
image.
use Pythagoras' theorem,
Application of the work energy theorem, WET.
that just
From the
tells
work
us
energy
that
theorem, the force
AP
F is given by
squared
F equals
plus
frac
PR
times KE,
squared
where
is
KE
AR squared.
equals kinetic energy, S equals stopping distance.
And
I'm
then,
given for object
so
A,
here dn
FA
is the
frac
diameter of the nth
100,000,
circle.
0.10.
So here,
For
this
object
just
B,
tells us
FB
that
equals frac
this 1 minus
225,
d1 over
1500 equals
2, that's
0.15
AP.
text makes n. And force ratio frac FA,
And then PR is just
FB
1.
equal frac 0.10, 0.15.
And then AR is 1 plus
I'm a box
D1
frac FA,
over 2.
FB.
Square
Would
that
you
whole
like a
thing.
PDF version of this explanation?
And then go ahead and solve this for D1 to get D1 equals 1/2. So then there, let's go on to the next page. So using the fact that the same type of reasoning, triangle PRB is right triangle. So once again, by Pythagoras, this time we'll have 1 minus, so first let me use the letters. Excuse me, so this is PB squared, PR squared, BR squared. Now using our D's, this is D1 plus D2 over 2. This is all PB. But then PR, that's just 1 squared. And then BR is 1 plus D2 over 2 squared. Go ahead and solve that for D2, and you'll end up with 1 over 6. We could keep going on in this fashion, and similarly, you can go ahead and look at triangle PRC. This is a right triangle. So let's do one more value of D. So this time, by Pythagoras, you get PC squared plus PR squared equals CR squared. And then this would become, using the D notation, D1 plus D2, D3 over 2. That whole thing would be squared. 1 squared, that's PR is 1. And then on the right-hand side, 1 plus D3 over 2, quantity squared. And this will imply D3 is 1 over 12. So let's go on to the next page, and let's just observe the values that we've already found. So here it looks like if we had to guess a pattern, 1 over, this is 2, we could write that as 1 times 2. 6, we can write that as 2 times 3. 12, 3 times 4. And using this pattern, it looks like dn, the diameter of the nth circle, should be 1 over n, with n plus 1 there. So this is true, and it can also be verified using mathematical induction. So here, the next step will be to verify this fact using induction. So the first one would be the base case. D1 equals 1 over 1 times 1 plus 1. And we know this is true because we already computed d1 using the geometry and we had 1/2. So the base case for the induction is true. Let's go to the next step. So here we suppose dn is 1 over n plus 1. And now we'll look at, we want to show that the formula is also true for dn plus 1. So that's what we would like. So here, let me take a step back. So here we would use Pythagoras theorem again. So we'd have some triangle PRN. Let this be the center of the n plus 1 circle, Cn plus 1. So this triangle right here would be another right triangle. So we use Pythagorean as we have been all along. So by Pythagoras we have nr squared, pr squared, nr squared. And I'm using the d notation, nr, we can write that using the same pattern that we've seen all along for the exact same reasons, using the picture. So that's nr, then we square that. PR has been 1 all along. And then the right-hand side, following the usual pattern, which again comes from the geometry that was given in the figure. Now I'm out of room here, so I will need to go back to the next page. So this implies, that's a sigma up there. I'm getting a little sloppy. That's the sum. I equals 1 to n di. All I'm doing is just rewriting the sum so that we can see how to use the induction hypothesis. Oops, that's a 2 up there. So now we'll just keep working with this. This is equivalent to 1 minus. Now, how can we rewrite this? We would like to rewrite this sum, so we know di using hypothesis 1 over I plus 1. This is an important step right here. We're replacing the di with this. So for the induction, we assume that the formula is true. This is also known as strong induction. We're assuming that the formula is true for all the values up to n. So since this sum is for I from 1 to n, the hypothesis holds for these d values. That's why we replace it with the fraction. But then we still add the other term at the very end outside of the sigma. And then we just rewrite everything else as is. Now our next step would be to go ahead and compute this, but this is a telescoping sum. So if you go ahead and evaluate that sigma, and again I should have parentheses around that. If you evaluate this sigma, you'll just get 1 minus 1 over n plus 1. And then now we're still have dn plus 1 over 2 squared plus 1. 1 plus, we're almost there. So I'm going to go on to the next page. So now we could cancel those 1s. And Now we cancel the double negative to get a positive 1 over n plus 1. You square that, add 1. Right hand side, been the same the whole time. Not going to change it now. And now we'll just solve this for dn plus 1. So let's square both sides. And then FOIL this thing out. dn plus 1 quantity squared all over 4 plus 1 equals 1 plus dn plus 1 plus dn plus 1 squared over 4. And then solve this for dn plus 1. And we have dn plus 1 equals 1 over n plus 1, n plus 2. So by mathematical induction, we've shown dn equals 1 over n, n plus 1 for all n, for all natural numbers n. So here we have noticed that, so going a step back, this gives another geometric demonstration of example 7. Which says that the sum I equals 1 to n of di equals 1. So in other words, the sum of all the diameters equals 1. And that's our final answer.